Welcome everyone to this session on model-driven robotics for this year's ROS Industrial Conference 2020. My name is Dr. Bianca from Fraunhofer IPA in Stuttgart, Germany. I will be your host for the next 1 hour 15 roughly. Before we start the presentations, a few words about today's conference format. Also, most of you may already know from yesterday. We will have 3 presentations from 4 speakers, I think, each about 20 minutes plus question and answers, followed by a joint discussion round of about 15 to 20 minutes. All of you following us at the conference website should have a live discussion box at the right of this session's page. Please post any questions or comments you may have for our speakers under the questions tab in that box. I will read the posted questions to our speakers either directly after the presentation or at the final discussion round. In addition, you can vote on polls posted by our speakers. With that out of the way, I have the pleasure to present our first speaker, Professor Ricardo Sanchez from the Technical University of Madrid, where he is a professor in automation control and the coordinator of the Autonomous Systems Laboratory. His research work focuses on intelligent control systems and, more specifically, on system autonomy augmentation by means of self-awareness and self-control. Today, he speaks about his work on meta control for ROS-I systems. Please, Mr. Sanchez, the floor is yours.
Well, I'm Ricardo Sanchez, professor at the Technical University of Madrid. I'm speaking here on behalf of Carlos Hernandez, who was meant to be here. And I expect I will do my work properly. So I apologize for anything that I say wrongly or that I miss. I'm going to talk about a project that we have just finished, that is the ROS project. I will describe basically the approach that we have taken there and some of the results and the demonstrations that we have produced. Well, ROS is a cascade project from the European project ROS-I. This has been a 1-year project, very short indeed. And the focus of the project is that we try to address special circumstances in ROS-II systems, so to say. When we need to write logic about an application and something happens, we need to write special code to handle these situations. And when we are writing applications that are complex, like ROS and ROS-II applications, this results in very complex software interleaving that hampers maintainability and understandability and reliability of the application. So the idea that we pursue in this work is that systems engineering knowledge can be exercised at runtime. Basically, this is well known. We are building models, and we are building models that we use at runtime. But the models that we build are not just the models of the system as built. We try to build models that capture engineering intentions, in a sense. So we want to capture knowledge about how the system is meant to behave, in a sense. And we use these models to do runtime adaptation, basically. The general objective of the project is to extend the ROS-I model-based approach into runtime for ROS-II systems and leverage it to provide a uniform and general solution to the problem of handling special circumstances using architectural self-adaptations of systems. And for this, we use ontology reasoning and functional description of architectures. In the project, we have 3 objectives. One was to create a scalable solution for robust and resilient robot skills using architectural adaptation at runtime. We also wanted to demonstrate the value of the ROS-I model-based approach to robotics in the case of ROS-II systems. And also, we also wanted to demonstrate the value of ontologies to support all this process from engineering to runtime as a main asset in the model-based engineering toolbox. As results, we have produced a software framework and 2 pilots. The software framework contains a domain model and associated ontologies in this context of functional adaptation of systems, basically. We provided a meta-control architecture that can be deployed over systems, a model-based systems engineering workflow using these assets. We created also a language to specify skills in ROS-2, and we create some tooling using Xtext for supporting this workflow. The two pilots that we built, one was academic, a social robot running in a university, and the other one was an industrial application from Bosch that was a vacuum cleaner. The overall approach follows the Moses three-layer concept that we have basically meta elements, meta structures that are, so to say, absolutely general. And then we have a second tier of conceptual sets in the robotics domains, basically. And then we finally have a content in the particular ecosystem when we are working. And this is, in our case, the ROS-2 ecosystem. So we provide tooling to create an application. The application appears here at the right, that is based on ROS-2 capabilities. In the case of our demonstrators, the capabilities are basically navigation capabilities for robots. And we create a layer of meta control that enhances the adaptivity of these skills at runtime using knowledge that we create from models of the system and models of the intentions of the designers, of the system architects concerning the capabilities and functions of the system. So we leverage models at different levels to create runtime reasoning over other types of models that are basically ontologies to adapt the system at runtime. One of the problems that we fought in this project was we were addressing a problem of harmonization of conceptualizations in different contexts. We were dealing with Moses, obviously, we were dealing with ROS-2, and we were dealing with previous work that we have done concerning systems engineering of adaptive systems. And this was a major problem, but we think that we finally found a way of coupling these conceptual models through two basic elements. One was the skill definition as an abstraction of capability, and the second one was skill realization as a concrete implementation in a domain-specific deployment platform that in our case was ROS-2. This is the domain model that we created for the project. The domain model contains basically three parts. One part relates to the mission that the robot must perform. Another part deals with the system, that in our case is a navigation system in ROS-2. And one part was the meta-control domain, that was this intermediate capability that provided the runtime adaptation that was needed for, so to say, match the concrete realization of the system at runtime to the needs for the mission and the tasks to be performed. Our framework provides several capabilities concerning concrete application, in our case, navigation capabilities, also related to the capabilities for system generation and adaptation at runtime, capabilities for runtime observation of system state and diagnosis, and capabilities for runtime adaptation and control the realization of a concrete implementation. This is a drawing of the final architecture as deployed with the components that created the application. We have here three types of elements. One element is related to the application, that is the gray elements are basically navigation specific elements. Another one is application specific concerning the specific application, in our case, the two pilots, the social pilots or the vacuum cleaner pilots. And the rest are general, domain neutral, and application neutral assets that we can reuse to control the application. In a sense, basically what we have created is an intermediate layer between the mission component, the mission coordinating component, that in our case is a behavior trees component in ROS-2, and the concrete realization of a capability in the robot, for example, localization or movement or obstacle avoidance or planning, we created an intermediate layer that matches the task with the concrete skills that are provided by the runtime system to provide the capability. So the mission of the metacontrol is to instantiate and runtime a system that matches the tasks, the intentions of the designer with the concrete realizations of the system that perform that capability. In the project, we also have created some model-based tooling, basically 3 elements. One language for system architects to describe the application, basically. A library of skill definitions that can be reused from application to application. In our case, just this library contains navigation skills that can be reused for navigation applications in ROS-2. And finally, some tooling for transformation, automatic transformation of the model described in the language into the runtime models that the system is using during operation. Basically, these are 2 things. One are YAML files for the realization of the system that we use a ROS-2 package that is the mode manager from Bosch to control realizations. And another one element that we use at runtime is a knowledge base based on the ontologies that we have created in the project to be used by the reasoners, runtime reasoners, to reason about the actual performance and possibilities of adaptation. Well, the language basically matches these two sides of the coin. The skill definitions that are general in the sense that they provide ways of achieving fulfilling tasks, and the skill realizations that are platform specific. In our case, there are ROS-2 implementations, and the language lets you match these 2 views of the skill, so to be able to automatically generate the databases and the models that the system uses at runtime for reasoning. Concerning ROS-2, we have used basically a collection of packages, but mainly 2 of them. The focus of the work was the Navigation 2 package. This is a very complex and sophisticated meta package for ROS-2 navigation robots. Here you can see the robot running at the university, one of the robots that we use for the demonstration. And the other package that we use more in this project was the system modes package from Bosch. That basically is an extension of the node life cycle of ROS-2, basically of the active state of the ROS-2 life cycle, node life cycle, to create, so to say, ways to handle alternative configuration at runtime. So we use these system modes to basically instantiate the skills, to have realizations of the skills at runtime, so we can exploit them and change between them using this particular tooling. This is the platform-specific layer of adaptation, basically. The 2 pilot implementations that we built, as I mentioned, one was a social robot in the university, going around and confronting special circumstances like battery draining or laser failures or narrow passages or cluttered environments or people around. These circumstances were handled by reconfiguring the navigation to nodes, so to deal better with the particular circumstances that the robot was dealing with. And the pilot from Bosch was a vacuum cleaner that has to be, so to say, resilient and robust enough to be used by people without many understanding of ROS-2 workings. So to summarize, we have produced a general meta-control framework to perform runtime management of robot skills. We have performed a separation of the task as thought by the engineer and the realization as implemented in ROS-2 systems. We have created a runtime reasoning mechanism using system knowledge to reason about this matching between goals and objectives of the system and concrete realizations. For this, we have used ontologies to orchestrate all the systems engineering knowledge all around the life cycle of the construction of the system. We have deployed this over ROS-I systems, in particular over navigation 2 and system modes packages. We have demonstrated this into robot navigation pilots, and we have created some tooling for model-based system synthesis and runtime system adaptation. The benefits of this type of work are many. We have addressed different key performance indicators concerning engineering effort, concerning maintainability, concerning availability, and whatever. But from my perspective, the biggest contribution of this kind of work is concerning the engineering time that is needed to create systems that are resilient and are robust enough to confront the circumstances of runtime. So my final conclusion is that the main value of this technology is to reduce the TTM for manufacturers to create systems that are dependable and perform autonomously in their environments. And that's all. Thank you very much.
Thank you very much for this interesting presentations. We have time for a few questions. So let's see if something was posted by the audience. No, what I have actually a few questions myself. One is, to what extent do you think can this technology which you have presented here with these meta layer in between the task of the robot and the actual execution engines be generalized away to other systems beyond robotics?
Well, as I mentioned, we have different levels, and the central core that is basically the meta control elements are totally general because they are based on systems engineering concepts that are basic and are totally cross-domain. Some of the parts that we have built are very, very specific to the robotics domain and in particular to the robotics navigation domain, and some are very specific to the ROS-I particular domain. But in general, the main assets that we value more in this project, that is the languages and the transformations and the meta level ontologies, are totally domain neutral and are universal in a sense.
Okay, thanks. There's another question from the audience. So what role do ontologies play? Did you develop that yourself and use OWL to describe them?
The ontologies play two roles in our system. One is to provide a vocabulary for the whole life cycle engineering of the system, providing concepts. I mentioned some of them. Well, we have different ontologies in this project. Indeed, here we have some of the terms that we are using in our ontology. For example, function design, function grounding, that are related to the skill and the skill realization that I mentioned, that are taken from the role Moses context, objectives and roles of the system. So we have ontologies that are used at the level of supporting the whole workflow in a sense. And we also use ontologies as knowledge bases for runtime reasoning. We have these two roles. And some of the ontologies are, so to say, written by hand. So we have, for example, the MROS ontology that is written by hand and captures all these concepts related to system adaptation to match realization to function and mission. And we have also, that are handwritten, so to say, but we have also ontologies, for example, ontologies that are used at runtime that are generated from system models to be used by reasoners at runtime. We use the Pellet reasoner, Pellet OWL2 reasoner to do the reasoning, to reason about the state, to reason about the possibilities, to decide basically about what skill realization best fulfills the quality of service needs of the particular realization now. So ontologies play two roles: supporting the whole process, in a sense, conceptual background for the whole thing, and runtime assets for reasoners.
Okay, thank you very much again for your presentation and answers. We need to move on to the next speaker.
Thank you.
The next speaker is Mr. Ansgar Rademacher from CEA List in France. He is a research engineer at CEA with about 15 years of experience in model-driven engineering. in particular with code generation from UML models. The talk will also be given by his colleague Matteo, also from CI List, with a strong background on model-based design of software architectures for mobile robotic manipulators. Both are involved in robotics projects and recently coached Rob Moses ITP projects. Please, Mr. Rademacher, the floor is yours.
Yes, thank you for the introduction. So I'm now sharing. Can you see my presentation?
Perfect.
Yes. So yeah, thank you for the introduction. So I will talk here about Papyrus for robotics, and the work presented here is work principally of the CA Rob Moses team. So that is consisting also of Matteo, who will also present a parts today, and Tuasca Espinosa and myself. So why are we doing model-driven engineering? And we are doing it because we observe that robotic software engineering is still, in many cases, a kind of craft. So it's a bit less systematic and more ad hoc as in other domains. And there are different incompatible component-based frameworks. With ROS-I, well, we are already on a big step forward towards a framework that is very widely used. But there is still also a code-centric approach. So you're coding, you have some description files, but the most parts of the application is still coded. And if different people are involved which having different skills, then there are no clear interfaces defined between these peoples. And this was one of the original motivation to start the Rob Moses projects. And as Ricardo already talked a bit about Rob Moses and the idea that you have different tiers, and there's the ecosystem structures at the highest level, and more important for us in tier 2 and tier 3 aspects, where you define, for instance, system-wide or generally accepted service definitions. You have so-called data sheets that help you to define if you're doing components that are a machine readable and partly also human readable definition, what the component does look like, and if we are going, for instance, towards a kind of marketplace, that will help us to get the key properties of such a component, then selecting it and using it in your system. And as I said, there are different roles, different players in defining such a system. There are also validation aspects, validation verification, there are safety aspects. So it's important to identify these different steps inside your system and have composable models to achieve your final system architecture. And in order to really have something that runs in the end, you also need some code generation and deployment mechanisms. And that is why we started to work on Papyrus for robotics. And by the way, this work has already also been supported by a ROS-I project called ROS-MDD. So it was a focused technical project of ROS-I that enabled us to add ROS2 code generation to Papyrus for robotics. So what is Papyrus and Papyrus for robotics? Some of you may already know Papyrus, which is an open source model-based engineering tool. It's integrated into Eclipse. and it's based on standards, so we don't have proprietary non-compatible extension, but you have a pure OMG UML standard and some OMG standardized extensions such as Smart. But it is possible to customize the tool to address domain-specific concerns. And that is what we have done with Papyrus for robotics. So we have done a customization for the robotics domain, and we aligned it with ROS-I with respect to the modeling artifacts, and we added tools for code generation which address specifically ROS tools. We also have some support for runtime, or not runtime, design time assessment of certain criteria, so you can specify some safety concerns and validate that. And here on the page, you see some references on wiki pages, and there's also a YouTube channel of Papyrus on which we have posted some Papyrus for robotic tools. You also have some, oops. What happened?
We see your editing view now.
Yeah,
somehow dropped out of full screen.
I dropped out of full screen and okay.
It's back in full screen.
It's big. Okay. Don't know what happened. So here you also have some testimonials and success stories of people who used it. Here you see a similar picture that Ricardo has shown with the different tiers and the different people that are involved in these aspects. For interesting aspect is that the service definition is considered at the tier 2 level, so that is a robotic expert. And if we are doing these service definitions at this level, this means we are kind of standardizing it for the domain, and thus fostering interoperability and reuse. And in our case, we reversed all the service definition and services and messages that already exist in ROS-II to have a standardized way of doing this. Well, there's a component definition in which you create a specific component and an implementation for it. The system builder aggregates a system, and there's also this aspect of skill definition, also in Ricardo's talk already. And then you can specify the behavior of such a high-level task by using a behavior tree. And in this context, you might do a hazard and risk analysis that is associated with a specific task. We have some videos on this. You might check off that offline. So the different building blocks of R2, well, you have an interface, HMI interface integrated into Eclipse. There's some support to do reverse engineering. We have code generation, and we have some safety analysis mechanisms. Here on this page, you see an example system that we obtained by reversing the ROS-II navigation stack. There's, for instance, here this Monte Carlo AMCL component that is part of the stack. Here I show you another quite complex example that has been done in the context of an ROS-I ITP, so an integrated technical project. And there is this arm assist robot that Technalia developed, and they are modeled all the different components that are coming with the system. Here on the right-hand side, you see also some contracts. And here this shows you that it's possible to also define some more complex systems with their tool, but I'm now returning to some very, very simple ones. So here on the left-hand side, you see some model libraries where you will find the data types and service definitions that are part of ROS-II. So we have here some models where you see a point, an occupancy grid, map metadata, and these are exactly the same data types that you find in ROS-II. And we have obtained this by reverse engineering. And here you see on the right-hand side this AMCL node, and the ports are typed with these service definitions that can be found on the left-hand side. There's also a link with Eclipse Cdt. So if you have modeled your component at one place at one moment, you need to write also code that implements the callbacks when you define here, for instance, the port with the initial pose called initial pose that gets a pose and then needs to react on this pose information that it gets. So you need to write code at some moment, and we propose to do that with the CDT, so the Eclipse integration of the C++ development tools. And for those that also want to change some of the model properties by editing the code, this is possible to some limited extent that you can here, for instance, change the name or declare parameter, and it will get updated in the model. If you have time, I can show that later on live. We are not only generating code, but we are also generating the build files. So there is the package XML and the CMake list that you all know that needs to be generated. And we configure an Eclipse Cdt project that is automatically configured for doing the Qualcomm build. And we also generate launch scripts which contain suitable remappings. Why is remapping needed? Because you might have some components that you are instantiating multiple times, for instance, here, distance sensor, and you have two instances of the distance sensor that you are connecting to our controller, and you need to make sure that the information from the first instance of the distance sensor is going to one port and that from the other distance sensor to another. So while we are reusing the same component, we need some reconfiguration to remappings to make sure that the communication follows our model. We also take care of parameter configuration. So we are generating the YAML files in which a user can override some default values, default parameters values specified on the model level. And the generated launch script we have generated a normal variant and one variant that automatically launches a component. And this is quite useful for testing. With respect to the Eclipse integration, we also offer the possibility to start a node in debug mode. So we integrated that with the CDT debugger so that you can debug your application from Eclipse and you can see how your nodes are launched by using the Eclipse console. And in the context of ROS-MDD, we did a validation with two use cases. So on the one hand, we had the navigation, a navigation use case, which we executed in simulation. On the other, pick and place application in which we used our EasyBot. This was also a CA pilot in the Rob Moses project. So we had these two case studies to show that our reverse and round trip mechanisms work. And with respect to the pick and place task, we particularly developed and evaluated the execution of a behavior tree. So Matteo, I don't know if you want to tell some words about the task execution and monitoring with a behavior tree. No? Okay, we will do that later. So you have principally a sequencer that is coordinating, executing the behavior tree and using a coordination interface to control one or more components which correspond to ROS-II actions that that get called by the sequencer. We will show a video on using this mechanism, because one of the interesting aspects is that you can see how the behavior tree is executed. You can see in which state the behavior tree is at a certain moment when you execute this behavior tree. And there's another interesting aspect that you can define hazard and risk analysis table and associated it with task and skills. So a skill of a robot, for instance, to do a certain movement or to open or close a gripper, has potential risk, and we are associating this risk with a skill, and then we automatically get a list of relevant skills when we define such a behavior tree. And at the leaves of this behavior tree, we have these basic skills that are executed by a robot. Here on this slide, I summarize some of the enhancement that has been done not by us, but by Rob Moses' integrated technical project. There was two projects conducted by Technalia. The first one, called EITUS, we supported fault injection, and we can simulate that's the behavior of a system, and one where we automatically inject faults and see how the behavior of the system deviates from the golden one without any faults. And the second one is the possibility to have contracts and assertions on the model level, which help us to perform some safety analysis. There are also two other projects in the context of safety. So in the project for scope, we look for verified system properties. So you can have here something like an invariant that always has to be true. Associate that with the behavior tree, and we use, for instance, the Othello language to do that. And in context of for Samara, you see here the links. We also have a look at the hazard and risk capabilities. So what are the contributions of Papyrus for the ROS-II community? We have a model-driven approach that differentiates the roles of several stakeholders that are defining a system, and we have well-defined interfaces between these roles. When we are modeling a component, we explicitly specify on the model level and then in a data sheet what are the services that a component requires, what are the services that it provides. And we can then generate code for ROS-II, including the build and launch files. And I think this is an added value for people that are starting with ROS and don't know the subtleties of the syntax. And we have an integration with model-based safety. And if you want to use it, you do not have to start from scratch. You can access existing ROS-II messages and services. We also have the possibility to reverse existing ROS nodes from a workspace and get some component definitions already. And well, if you are preferring to code, we still have this option that you open a CDT editor and do some of the changes on the code level. Yeah, here an outlook on our roadmap. We are using it currently, Papyrus for Robotics, in several European projects, and it continues to be developed actively. We are planning to support composite components to model more complex systems, and we are examining the link with a ROS-II based automated planning solution. And certainly the path that Ricardo showed in the previous talk is very interesting for us. We also consider eventually to look at real-time support with a model of computation that we already applied in a different project. So that includes some scalability analysis and the assurance that the system will respect deadlines when it runs. Yeah, thanks for your attention, and I'd like to have some questions now or after the next talk and at the end of the session. Thank you.
Okay, thank you very much for this interesting presentation. With considering time, I would like to postpone questions to the general discussion round and move on to our next speaker. The next two speakers are Mr. Shashak Sharma and Jim Lee from MathWorks. Shashak Sharma is an application engineer at MathWorks Germany, and Mr. Jim Lee is a senior technical project manager for robotics at MathWorks based out of the US. They will present their work on interoperability aspects of Matlab with commonly used open source tools like ROS and Ricardo in the field of autonomous driving. Please, Mr. Sharma, the floor is yours.
Hello, everyone. Thank you for joining our talk in the ROS Industrial Conference. I'm Shashank, and together with my colleague, Vijay Lim, I'll be presenting today a talk on co-simulating Carla with Matlab using ROS for model-driven automated driving systems development. Before I move forward, I would like to specially thank my colleagues, Christoph Hahn, Steve Schaefer, some students from Technical University of Munich, M. Kerish, M. Sattar, and A. Pasach, and Mr. Philip Kopp from the Chair of Computation and Engineering for collaboration in the early proof of concept in this regard. So now let me start with talking about autonomous systems first. So autonomous systems may have a mix of multiple cycles of synchronous processing for more precision control, as well as asynchronous interface for communication of data and events for inter-process synchronization. Autonomous systems control may also require parallel or distributed processing, running on multi-core and GPU for high resolution and multi-rate sensor and perception processing. So it produces coordinated motion of multi-degree of freedom actuators in autonomous systems. So it's very complex. There have been several robotics frameworks that have appeared which propose some solutions to design and develop a distributed system of an autonomous system. Now, ROS is an enabling technology and quite popular one to develop such complex intelligent system. With the given system design requirement, ROS provides a common framework to design, simulate, and prototype robotic applications. With ROS, you can also analyze log data, design algorithms with variant handwritten codes, and visualize and debug your results. You may need to rewrite source code for production, though. Now, by connecting Matlab and Simulink with ROS, it allows you to perform system-level simulation with requirement traceability. It also provides you a rapid and iterative design processes with many of the tools Matlab and Simulink has for autonomous systems. You can also generate certifiable code for production and not just C++ code. You can also, if needed, generate HDL code out of Matlab and Simulink for deployment on more energy friendly hardware resources. So I will not delve into those details. Today's focus is how we bridge ROS with Matlab and Simulink for an application related to autonomous driving. So now let's see our agenda first. So today's agenda, I will begin by giving you a brief overview of ROS and ROS2 workflow with Matlab and Simulink. Then I will go into details about co-simulating Carla with Matlab and Simulink using ROS. I will talk about autonomous driving systems development also in this context. And then I will briefly talk about what is possible beyond co-simulation and summarize our talk today. So let's go into the first part, how the ROS and ROS2 workflows looks in combination with Matlab and Simulink. Some of you might remember this was the core of my talk in the last year's ROS Industrial Conference in Stuttgart. And today I will be giving you a brief one-slide summary of that topic. If you have interest in knowing more about this workflows, then feel free to contact me. Alternatively, there's also a YouTube video from ROS Industrial that you can look from the last year's conference. So on the right-hand side, I'm sorry. So on the right-hand side, there's a traditional ROS-enabled system that might look like there's a host of ROS-enabled simulators or hardwares, and with nodes that would enable autonomy, visualization, and so on. Then on the left-hand side, Matlab and Simulink offer tools for autonomous systems development. Some of you might be familiar with our tools. Simulink, Stateflow, Matlab are used widely for such purposes. So for autonomous systems development, systems should have functional components of sensing, perception, planning, and control. And now we have a tighter bridge to ROS from Matlab and Simulink. So basically, there are three workflows how we can connect Matlab and Simulink to ROS. The first one is a ROS bag import for offline analysis. So you can read in ROS bags into Matlab and Simulink and do some post-processing. The second one is ROS connection, which enables you to enable a live connection between ROS and an instance of Matlab for algorithm development. So this enables you to quickly debug your applications. And I think one of the words you heard in the last presentation was it also enables you to see the engineer's intent. So as you move through the application, it shows you different states where you are in or which part of code is being executed. So it really helps you to understand it from a system level point of view, as well as also what the engineer intends to do with the application. Now, after that, you can, once you are ready for deployment, you can generate either C or C++ node, and you can also directly generate a ROS node as a standalone, which no longer requires Matlab and Simulink to run. Now I want to point out that beyond just bridging ROS with Matlab and Simulink, you can also complement traditional ROS solutions with Matlab and Simulink tooling. I have more details if you want to do it. Due to shortage of time, we cannot focus on all the workflows or the support, how can we bridge and complement the traditional ROS solution in detail in this talk. Now, coming to my next topic, let me talk about how we can co-simulate Carla with Matlab using ROS. So in this respect, let me first talk about the 3D simulation for automated driving in particular. So as you know, autonomous driving is very similar but slightly more complex in conjunction to, say, mobile robotics development. There's also safety critical factor involved and lots of regulations, plus interaction with lots of vulnerable users such as pedestrians, cyclists, etc. So in order to test complex algorithms, there's a very strong need to virtually validate those scenes. You also need to have an environment where you can realistically test and gain confidence in your algorithms before you go out into proving grounds or into the real world situations. Such a 3D simulation requires modeling sensors, visualizing vehicles, as well as other vulnerable road users, You can generate and record synthetic data and simulate scenes. There's also a need to programmatically create scenes and scenarios in order to cover a large amount of solution space that might or might not be possible through real-world testing. So in this regard, MathWorks already offers a complete solution, which involves using 3D simulation and modeling sensors. However, a lot of people that work on these problems do not rely on a single tool, and rightly so. So autonomous driving is a really complex application, and for that, you need more than one tool, maybe during the different stages of development, and you need tools that can interact and interoperate with each other. And in this respect, many of MathWorks customers, they like to use our solutions at some point of time, and they would want to use parts of those solutions with other tools, which also includes ROS-based codes or maybe tools like Carla at some other point of time. So that means interoperability plays a very important part in the whole process of autonomous driving. Now, let's look at the example application that we are talking about in this example. So in this case, we are talking about a highway lane following example. This is one of our reference examples that we also provide with our toolbox. What is it showing here? This is a Simulink model, or also you can say a system model of the whole example. We have parts for perception, planning, and control implemented in Matlab and Simulink. So vision, perception part, sensor fusing data between camera and radar models, then having a planning and controls module, and also implementing a vehicle dynamics module. One of the most important part that we just discussed now is the scenario component, where you have a static scene environment, vehicles, actors, and other sensors, and together all these components constitute a scenario. So in an ideal world, MathWorks offer all these components if you want to use them. However, a lot of our customers use either scenarios with different simulation environments, and or they have parts of code which are written in Simulink and Matlab, and parts which are written in C and C++ and integrated into Simulink. So I would like to focus today on the part related to scenario-based testing and how we do it inside MathWorks, and then how we do it with Carla using ROS-Bridge. So a brief example of how that simulation could look like is in the slide. So here we are co-simulating with Unreal Engine directly. And if I click on the video, we see a highway lane change maneuver where we have an ego vehicle in blue, and then there is a red sedan that is cutting off. And on the right-hand side, you see when we record those signals and we replay, we can see and analyze a lot of things, such as yaw angle of the target vehicle, which is the red sedan, and like how our absolute velocity changes as the red vehicle cut in. So this is helpful for analysis or also virtually test. Then there is another example of the same algorithm in a different scenario. So like how you test those scenarios in different settings is like lane following on a curved road. So if there is a strong cut-in maneuver with a vehicle, then and you have safety requirements of maintaining a safe distance, then how your algorithm would react. So these kind of virtual environments give you a very good overview on how you go through about your solution in the real world. Now, based on, I talked a lot about scenario-based testing, and I will now talk about Carla, because Carla is one of the most popular open source simulators for autonomous driving. It is also based on Unreal Engine 4. So the scenes or scenarios in Carla would look very similar to what I just showed in the previous slide. It also involves a rich 3D environment, but also imports semantic information from OpenDrive, which is again a standard for defining roads and static environments. So this enables you to create a very rich 3D environment to test driving proficiency in realistic driving simulation. Carla is an open source tool, but it is strongly funded by companies like Intel and Toyota. And they're also learning from the best in the open source community due to them being part of OpenCV Foundation. And in my personal experience, one of the reasons why Carla is so popular is because it has good support with ROS for co-simulation with ROS. And due to that, a lot of people who are working on autonomous driving development, they start, and if they're working in ROS, which is also a very common tool used in the same environment, they start working in ROS and maybe start early prototyping in Gazebo or in tools like Matlab. And then when they have a need for non-production environment, but a very high 3D environment, they switch to Carla because it's really easy to switch to Carla if you're working in a ROS-related environment. So this makes it really popular for autonomous driving 3D scenario-based testing. Now, I talked about how Matlab and ROS interact using ROS Toolbox. And I talked about how like ROS has a very good connection with different sensors, simulators, and hardware. Now, if we take this concept, I talked about Carla has a good support with ROS. So this enables us, these two bridges enables us to interact with Carla using ROS as the communication platform. And the communication between a ROS and Carla goes with the help of ROS-Carla bridge. So first, we would need to subscribe specific nodes of ROS by using ROS Toolbox inside Simulink and by using Matlab, and publish all of the changes using publisher block inside Simulink. And this cycle continues with going back to Carla. With this, we leverage the best of both worlds. So in MathWorks, we have a lot of reference applications. We have specialized tools for the perception planning and control, and we have lots of V&V workflows and a very strong vehicle modeling. And you can also create custom sensor models. Going to Carla, Carla has very good assets. They have very good driving scenarios, sensor models, and can work in distributed mode as well. And you can programmatically change a lot of scenes and do a lot of scenario-based testing. So together, using ROS, it's a very good use case for co-simulation. Now, what we did is we did an example lane detection and following. We placed the necessary sensors to take the image. Then the second part was to read the sensor data using Carla ROS bridge. After that, we implemented our lane following system that I showed you inside Simulink and generate feedback to this algorithm. And lastly, the data bus package sent to the vehicle to change the vehicle movement. So these are the steps that was involved in co-simulating algorithm that is running on Simulink while the scenario running in Carla. So I will talk about some of the steps and try to show some videos in this regard. So first one is the lane detection and following. So on the left-hand side, you see some images from Carla. We get semantic segmentation image from Carla as well as RGB image. So we can then process that image inside Matlab and look for pixels in black and white. And based on that, we can generate, calculate the slope with respect to vehicles and straight edges. We can calculate some splines. And by collecting these slopes and steering angle history, we can predict how much steer we need. And yeah, we also draw and fit those splines to steer the vehicles. So I have a video which might not run. I ran into trouble at the last moment. So in the video, I meant to show how the steering maneuver looks like. So on the left-hand side, this image is being generated in Carla. Semantic segmentation corresponding image is also generated in Carla from the camera, but this processed image is being generated in Matlab as the video runs. So I wanted to show you in the video how this looks like in the process. However, I ran into last moment troubles with the video. I have another example where I talk about the LiDAR processing. So the original image is being obtained from Carla, but later on we can prune the image, LiDAR image, and We can remove some point clouds, do ground plane removal, and do some clustering inside Matlab. I have another example where we have on the bottom left a video from Carla, and then we are doing segmentation, like clustering of image, ground plane removal. We are clustering and then putting bounding box images on those LiDAR point clouds. And as you can see that as the car vehicle moves, you can see how we can process those images and point cloud processing in Matlab as we run a scenario in Carla. And this process can even more accelerated by generating code for the LiDAR processing algorithms as a C++ code. And you can also deploy that as a ROS node later on. So then in order to achieve a bit more faster processing. So as I mentioned, the live connection is, we can do live connection with Carla using a live instance of Matlab to analyze and iterate through your algorithm, but then later on, these algorithms can also be deployed as ROS nodes for a faster processing. So that interacts again very well with this ROS communication model, and Matlab can support code generation to that. So this was like some of the studies and proof of concepts, how we can co-simulate such a model and do a closed loop testing with different tools. If there are some interests in this kind of studies or in this kind of simulation, co-simulation using ROS with Matlab and Simulink, we would be very happy to discuss with you in offline after the conference. I would like to talk about some of other things that are possible beyond co-simulation. So another thing that with Carla works is how to generate the environments. And for that, we also offer Roadrunner as a product, which works with a large variety of simulators. And actually, Carla mentions Roadrunner as a tool of choice for in their documentation. If you are working with other simulators, then like which are ROS-based, such as LG, SVL, there is a similar workflow. We can also support a similar workflow. So in the end, we can leverage strength of each of the environments. So like using Carla's strengths to have a different variety of assets, scenarios, working with APIs to create a very strong 3D scenarios for autonomous driving, and well at the using MathWorks strengths to have reference applications, V&V workflows, scene creation, and using ROS as a communication layer, and also deploy code later on to the ROS. We can leverage both environments and use ROS as a middleware network. And this workflow is also not just limited to Carla, but to other simulation environments as well. And as I already mentioned, for Gazebo, we have a direct co-simulation environment. So Gazebo, we have one of the best co-simulation support. But if you're talking about autonomous driving, and there are different simulators that you're using that can connect with ROS, we can support those applications as well. We have different resources to get you started with. I have added some links that will help you later on. So I just wanted to thank you. And if there are any questions, I would be very happy to hear them. Thank you.
Okay, thank you for this interesting presentation. There were, as far as I see, no specific questions for this in the audience. So I would suggest that we directly move on to the roundtable discussion round. And for that, I would like to ask all speakers to enable their camera and microphone so that we can easily switch around. Before we go to the actual roundtable discussion, there was actually one question posted for the previous presenters for Papyrus, which I would like to ask before. And this is the task execution. Is the behavior tree for tasks auto-generated, or does it only support tasks in sequence, or have task planning, or you have task planning behind to plan how to execute a task? I think that's for Mr. Rademacher.
Yes, sir. Well, on our side, Matteo is the expert with respect to behavior tree, but there might have been an audio problem. Can you speak now, Matteo, or should I answer? Well, we don't. Do you
We don't hear
Matteo?
anything from you, Matteo.
Okay. Yes, well, we model the behavior tree, and the behavior tree. Well, by the way, I have also a short
can you hear me
video.
now?
Yes.
Oh, sorry. Okay, good.
Okay, I paused the video.
I fixed the problem. Okay, so the question was, I can try to answer if you like.
Is the behavior tree for tasks auto-generated?
Okay, the behavior tree, at the moment, the behavior tree must be modeled by hand. We have a dedicated view in Papyrus for robotics to model the behavior trees. Leveraging the concept of skill definitions that have been mentioned by Ansgar and Ricardo as well. That is part of the composition structure of Robotics that decouples the task level with the service level where the functional components are executed. So based on that, the behavior designer, that is a specific role that we envision in the ecosystem, can build manually the behavior tree with control nodes like sequence, fallback, parallel nodes, and so on. Very much like the nodes that are used in the nav2 stack in ROS-I. Not all of them, but a subset of them. And you can compose the skill definition to model the behavior tree. Then we have an exporter from this model in Papyrus to the format that can be processed by the behavior tree.cpp libraries that is used also in nav2 stack. So from the Papyrus view, we can export this model into the XML so that it can be executed. I don't know if this answered the question. In the next work that we are going to do, we are going to couple actually this part with PlanSys, that is a framework for planning systems on top of ROS-I.
Okay.
So this framework will give us a plan to execute, and we can convert the sequence of action from the plan to a behavior tree. This is a work in progress.
Okay, good. So I would like to then start the actual roundtable discussions, and I would like to ask everyone to try to give short answers so that we can at least have everyone heard for once. So I would like to start with one question actually to all speakers. We have seen quite a number of different modeling and simulation tools or frameworks today. So in your opinion, how do you see the current use of model-driven methods in robotics software development? Is it actually being used in the wider ROS community, or is it rather at a slow start? And I would like to ask first Mr. Sanchez.
Yeah, I think it is not used at all. I think my impression is that the tooling is so far from the real needs of practical implementations that real people building real robots are not using model-based tool chains to generate the systems. Models are used for some specific parts, but not in general to support the whole process and the whole implementation.
Okay, thanks. Mr. Sharma, what's your view?
So I would ask my colleague YJ to answer this question. Probably, yeah.
Okay, sure. So, thank you. As my colleague Shashank presented, so robotic and autonomous system area, so like become the more and more complex system. So model design, we see from our customer, they really the adapting a lot. So it's not really the one division kind of a work. They are working with multiple the team together. So they are using the same model from the concept design with requirement all the way to the system integration, and then you later on you are implementing to the hardware in a real hardware system. So from our observation, how they use model-based design, model-driven design for the autonomous system, we see really the user adapting more and more. That's our observation.
Maybe one line from my side. We do see people using model-driven robotics in different applications, not just in automotive, also in robotics applications. Different stacks have either need interoperability, but model-driven robotics and model-driven design plays an important part, especially when it comes to production.
Okay, and final in this round, Mr. Rademacher, what's your view on uptake of model-driven tools?
Yeah, I think, yes, as Ricardo said it in the beginning, up to now, it's not too many people are using it, I guess, because for building many systems, the advantages are not that obvious. But when we are seeing more and more safety critical systems, are systems where we have to make sure that some of the constraints are taken into account, that we have traceability. So for these systems, it would make a lot of sense to take modeling into account. And we try to have a small entry hurdle by providing already a lot of the familiar ROS-I environment and the service definition. So we hope that it will uptake in the near future, and that more and more people are using it because they see the advantage of having this separation of roles that we are promoting in Osmosis, this composability and the safety integration.
Maybe another question also to you, since you were active in Osmosis. There are different frameworks. So do you see a consolidation of frameworks already now, or will we live with many competing and also incompatible frameworks for the foreseeable future?
We try, of course, to achieve as much as possible some compatibility, and the data sheets well, to be honest, is not yet done, but the data sheets are one of the possibilities to make our tool, for instance, compatible with Smart MDSD from University of Ulm, which has been presented last year in a session here. So we hope that there is some consolidation, and as our tool is an open source tool, and then we will also try to do some more tight links with the work done in MROS, that we hope to see some consolidation here and some unification of the tooling.
Kind of follow-up questions, maybe for Mr. Sanchez. Do you think it's actually feasible to convert models from one framework to the others, especially when we look at these meta modeling, which we also has shown today?
You're asking me, sorry?
Yes.
Well, I think it is not easy, because when some concepts in the meta models are different, the work is difficult to automate in a sense. So I think, in my impression, we need to go back into more top-level ontologies and meta models to be able to fully support this process of tool integration or tool interchange. And indeed, I think that the work in top-level ontologies is critical for all this stuff.
Okay, thanks. Probably one final question I would like to actually pose to Mr. Sharma and or Mr. Lim. So we have seen many tools, and actually tools currently usually either focus on modeling, system building, or they focus on simulation. Do you see it as a general trend, or even as something to be desired, to actually combine these into one tool?
I will start maybe like first. So yes, this is something that is highly desired by people who use Matlab and Simulink, and that's why we offer a tool to where you can actually start with the system design, start linking traceabilities, then go into your development, then actually simulate, and then also work on the deployment. So in the traditional automotive sense, it's like V-cycle, but it now like the similar concepts in different to some different degree and with some constraints also adopted in agile development cycle. And people like if they have one tool to cover as much as possible, but they also want the flexibility to adapt and interoperate with tools at different stages of development. So this is what is driving our development in this area forward, particularly by system level design and simulation. And this is one of the strengths of also our tools.
Okay.
YJ, would you like to add?
Yeah, I echo same thing to the Shashank. So like modeling and simulation is not two different worlds. So you model your computational model, and then you go to the simulation, then and the same model you have, and then we heard about here this talk, people, there's an algorithm, there's the computational model, they generated the C++ code and C code. Then same your algorithm can use your target hardware. So it's not really two different ones. This is kind of we see they are in the same world. That's my answer.
Okay, all right, thanks. So unfortunately, we're slowly running out of time. So I would like to once more thank all the speakers for the presentations and your question and answers, and also for this nice discussion at the end. So once more, thanks again, everyone. And with that, I would like to close the session. See you next time.
Thank you, Björn.
Thank you.
Bye. Thank you.